Okay, many thanks for the invitation. I'm going to talk about the compactness of some logic. This is not a new logic in any sense. It's very old. It's a construction of Sahoron Shelah. But still, I think maybe it's not very well known. And a few years ago, for some reasons I will explain, I got interested in this logic jointly with Martin Ziegler. And in the end, we finished writing an article for the Bulletin of Symbolic Logic that appeared in 2020. So I'm going to talk about that. The logic is the logic of cofinality. The most well-known case is cofinality omega. So let me begin just saying something that maybe everybody knows. The cofinality of a linear ordering is the least ordinal alpha for which alpha has a cofinal subset of order type alpha. And is a standard topic in basic set theory that, in fact, it is a cardinal number. It is a regular cardinal number, the cofinality of an order. It's a characteristic of the linear ordering, which is useful for many things, for computations of the exponential cardinal function, for instance. Anyway, there is a way of extending first order logic, adding a new quantifier. Well, there are many ways of doing that. For instance, Kiesler studied the case of adding a quantifier to express there are uncountably many objects that satisfies the formula. And this was very celebrated because there was a completeness theorem and a compactness theorem for countable languages. There's a beautiful logic, and unless this is a big difference with what happened with the logic, I think, of Mostowski about the quantifier. There are infinitely many, which is has a very bad model theory. Anyway, there were some examples. There are many more, and this is just, in principle, a new example of a logic. So the quantifier binds two variables, x and y. And you can apply it to any formula. So this is a standard inductive construction of the language using quantifiers from first order logic, connectives, and moreover, you have this new quantifier. And the reading is the binary relation given by xy that satisfies phi defines a linear ordering of the universe with some specific cofinality. Well, the semantics is, this is the syntax, right? The syntax is just writing this new formula. And this can, of course, be iterated. So it's a finitary language like first order logic with this new quantifier. The semantic depends on the choice of a set, or even a class of regular cardinal numbers. So let's call C the class. Whenever you fix such a class, you have a corresponding logic. The definition of the satisfaction relation is standard in first order logic, and there is a step where you consider formulas with this quantifier. This is the key step to understand what's going on with the semantics. Well, the definition is that the binary relation defined by this formula, the formula phi may have more parameters, C bar, but we're looking at the place of x and y. So the binary relation defined is a linear ordering of the model without last element and with cofinality in C. So the C see maybe it's a huge set of cardinal regular cardinal numbers, maybe small. So there are many options for it. Okay, but the most popular case is the case where C contains just a single cardinal number, which is omega, Aleph 0. So in this language, you can express that a formula defines binary relation, which is a linear ordering of the universe. Up to here, everything this is something you can do in first order logic. Okay, there's nothing. But the added condition that the cofinality of the order is omega. This is the thing that is new in this approach. Okay, so this is the logic, this is the syntax, this is the semantics, and this is the most well-known case, logic of cofinality omega. This is very old, I told you. Shelah proved in 1975 that this logic is fully compact. Fully compact means that it satisfies the compactness theorem for any set of formulas. It doesn't matter the size, the cardinality of the set. So you can apply compactness to any set of symbols. This makes a big difference with the logic of Kizler about the quantifier. There are uncountably many where you get only compactness for countable sets. Here it is like in first order logic, it's fully compact. Well, you know, there is a theorem about this kind of systems of extensions of first order logic by Lindström that says that you cannot find an extension of first order logic, a proper extension, which is fully compact and has the Lewenhein's column property down to omega. So if this is fully compact, you should expect that the Lewenhein's column will fail, and it fails. I remember, I think there is a Lewenhein's column theorem down to omega 1, but not down to omega in general in this logic. But so it shares a lot of good properties of first order logic. So let's go back to Shelah. Shelah introduced this logic, and he proved that it is compact. But well, the proof of Shelah is to say in a sensible sense, it's not elementary. So to tell the truth, it's not easy to read. The article of Shelah sends you to some other article written in 72. But if you try to understand what's going on in these articles, you have to work very hard to see what happened. So the proof was there, but I don't think it is an accessible proof. So after Shelah, some people tried to write new proofs. There are different. So, for instance, Markowski wrote something with together with Shelah, and Ebbinghaus wrote a presentation, but none of them is complete. So, in some sense, all go back to the original article of Shelah. With Martin Ziegler, what we did was to find some elementary complete proof of the compactness of this logic. So it's a very old topic, but I think for the first time it's fully understood now. Well, I'm sure Shelah understood it, but I mean for the rest of the humans beings, is now I guess I hope easy to understand what's going on with this compactness proof. So this is the reason why we decided to write it down and to publish it. There was also Van Anen should also be mentioned, because Van Anen wrote a book, Models and Games, where he did many things. He discusses many logics, and in the end, he looked at this logic, and he presented a proof of the compactness in Kistler style. Kistler style is elementary, is nice, is kind of old classical model theory. This is what we did with Martin Ziegler, but Van Anen did it before. The problem with Van Anen proof is that it only works for countable languages. So Hodgins was, I think it was Hodgkinson who wrote a review of the book. He found a mistake. So the proof cannot be repaired, and it doesn't work. That's the situation. So this is the reason why we understood this. It makes sense to write a proof of this logic. Okay, the main ingredient that doesn't come exactly from logic, but helps to understand what's going on, and is we are going to use it in the proofs. So I'm going to present the proof. To sketch. I hope more or less people will be able to understand what's going on in this talk with the proof. But I'm not going to do every little detail. So I think you can go to the text to the article and check a few things. For instance, we fix a linear ordering, and there are two quantifiers that make sense here. One is the quantifier there are cofinally many x that satisfy some condition A. And the other one is the dual quantifier. Exactly like in first order logic, we have the existence and the for all quantifier, and one is dual of the other, can be defined exactly the same way. You get the other one that says there is a point starting at some point x prime. Everybody above x prime satisfies the formula A. This is the quantifier for all cofinally x ax. Okay, these two quantifiers are used. In fact, they can be written in first order logic, but this is not the point. They are used now to define a relation, a binary relation between two orders. We have two linear orderings, x and y, and G is a binary relation between them. We say that it is a connection if the following happens. There are cofinally many x with a property that starting at some point in y, everybody bears the relation G with these points in x. And to the other direction, there are cofinally many points in the other set y with exactly the same relation, but with the negation of G. Well, this make at the first sight seems strange, but it makes a lot of sense. If you look at the following lemma, two linear orders without last element are connected if and only if they have the same cofinality. So this is very powerful. On the other hand, it's elementary. It's not a difficult proof. I think it's full written in the article. It tells you that, well, to begin with, this relation is an equivalence relation to have a connection. It represents exactly what we want. We have, we want to control the cofinality of the other. For instance, so if you have two linear orderings with the same cofinality kappa, And then you have sequences which are cofinal. Say in the order X, you have X alpha, and in the order Y, you have Y alpha. And you want to define this G. Well, there's a pretty easy way to do it. Just you have to relate each point X alpha with Y alpha and everybody above Y alpha in the set Y. So it's like a triangle starting in X alpha and relating to Y alpha and everybody above. It works, for instance. This will show that when they have the same cofinality, then they are connected. There is a connection between them. There are some other ways of finding the connections, and there are more nice connections. But this is one of them. Okay, so we will do logic. So we are interested in definable connections. We fix an L structure. L is language, as usual in model theory. And we consider two definable linear orderings. Maybe the definition is with standard is with parameters. You have the order with phi and the order with psi. They are orderings of the universe without last element. We say that they are definably connected if there is a definable connection between the orderings. Definable with parameters, typically. And the first, well, the ingredients in the proof are standard. I mean, is classical model theory is just elementary change constructions, omitting types, theorems, and nothing else. Nothing else. This is the proof. I didn't tell you why I was interested in this logic. Maybe it's worth mentioning this. The point is that I wrote some article with Saharon Shelah on a topic about expandability of models. And this logic, the case of omega, the logic of cofinality omega, was used to find some example of a series of examples sharing a very interesting property. This could not be done with first order logic, so this logic was essential to solve the problem. And when we wrote the article, we wanted to publish it, and we mentioned the article, the original article of Shelah as a reference for the compactness of the logic. What happened is that there was a referee that said that in this article, the theorem was not proof. It was only a consistency result. So in the article, Shelah, according to the referee, proved that it is consistent with Zermelo-Frenkel set theoretical choice that this logic is fully compact. And well, this is against what Shelah said and what I typically understood. So I look at the proof, I look at the article, and I discovered that at the beginning of the article, there was an assumption about the existence of a large cardinal number. And then Shelah proved things in the article with this assumption. The question is that the things he proved was in the first section, or the first two sections, I don't know, and was another topic. What was about some logic that that was stronger than first order logic even for countable models and has some properties. I don't know. But in the last part of the article, Shelah addressed the logic of the cofinality. And there was no assumption at all about the existence of cardinal numbers. But the referee read the beginning of the article, and he insisted, and there was an assumption there. And there was no way of convincing him that there was not the case. So we decided to publish it in another journal. And I got very interested in seeing what was going on with this proof. So I talked with Martin Ziegler, and we started discussing the proof, and we found out this new proof. But usually what happens, sometimes referees don't hear what the author says. So I think to be a referee is difficult, but if somebody tells you very seriously that something is going on, you should, I guess, consider seriously the possibility that maybe you are wrong. This not always happens. Anyway, let's go back to our lemma. So the main lemma is about isolation of types. So this is fully model theory. Situation is the following. We have two formulas, phi and psi, which are not definable connected. So I assume they define some, both of them define some linear ordering without endpoint in the model. And I choose a new constant, and I consider the theory with all names for the elements of the model. And yes, I say that C is larger than everybody else in M. Well, this is a standard way of obtaining some elementary extension of M with a new element which is larger than everybody in the model we started with. Well, the claim is that this theory does not isolate the partial type that we can construct using the other relation, the order relation psi. Because there is no definable connection between them, you can realize one of them and omit the other one. Okay, so you can add some element which is larger than everybody in the order phi, and omit adding somebody which is larger in the other order. It's their main lemma. Okay, let's take a look at the proof. There is a fact concerning these connections. Has nothing to do with definability. It's just a basic fact that sometimes we can simplify the conditions to obtain a connection. So if you have a binary relation between two binary orderings, and from left to the right, you just know that there are cofinally many x having some relation with somebody in Y. And the second relation tells us that there is an lower bound and an upper bound x prime I. Sorry, that for every I prime, you can find some x prime, so that if you work over x prime and below e prime, then there is no connection between x and y given by G. Well, then if this is the situation, you can define G prime as here, and you get a connection between x and y with the properties that we fix at the beginning. Okay, we will use this. So in order, so what we're going to do is to assume that the type is not isolated. Sorry, that we assume that the type is isolated by some formula, and then we will find some definable connection between the others. That's and to find some definable connection, we use this fact. So assume that the type can be isolated by some formula gamma with parameters in M, and in this language, we have C, this new constant that can appear in gamma, so that gamma Cy isolates the type. So this means two things, that the formula is consistent with T prime, and that the formula implies the type. So it implies that Y is larger than everybody else in the model M. And then we claim that the relation defined by gamma has the two mentioned properties, to the two properties that for the corresponding orders. So we can call it G, and if we take G prime, we find some definable connection between them using the isolating formula gamma, and then we define it as G prime says. The fact that the gamma is consistent with T prime is the first condition. you can see that, in fact, the properties of C in this context go back to things that happens for arbitrarily large elements in M. So this is exactly what we need. For every element M, there is somebody. So there are cofinally many X in the model that have some corresponding Y in gamma. And the second condition comes from the isolation, so from the fact that gamma implies a type. So for each for each element n in the model M, you find some element M with this property. This is also easy to see because everything that T prime implies about C is something that there is a point where everybody should realize. This is standard things, for instance, in the Kissler proof of compactness, or in two cardinal theorems. The kind of things are very typically used. Okay, so this is the proof. So you will get some definable connection. Now, there is a corollary about this, which is the following one. Assume kappa is a regular cardinal number, and we consider a model and a language with a size at most kappa, and we fix a definable linear ordering of M without last element. Well, then we can find elementary extension of the model such that this order is not cofinal in the new model. So because we have added some new point above everybody, this is not cofinal, but any definable ordering of cofinality kappa, which is not definable connected to the first one, will be cofinal in N. And the proof is, so the proof uses a version of the omitting types theorem, which you can find in Chang-Kissler book, which is not typically applied. So it tells you about omitting types in larger languages. And what the difference is that instead of considering formulas isolating types, you consider a set of formulas isolating the type. And the condition is that the set of formulas that you consider should have smaller cardinality. Okay, so the interesting thing is that this omitting types works, and in our case, and we are discussing linear orderings and using regular cardinals, it can be reduced. This set of formulas can be reduced to one formula. So there is a connection with the standard omitting types theorem in this context. So the situation is the following. You take the theory with a name for everybody in the model, and you say that there is somebody C, which is above everybody in the order of 5. And we know by the previous lemma that T prime does not isolate the types which we want to omit, because in the end, this is an application of some omitting types situation. So we want to omit all these types. They are not isolated, but in fact, we cannot do that because we are not in a countable language. But this is the point where this version of the omitting types theorem of Chang-Kissler help to solve the problem, because if you have a set consisting of an ordered chain of formulas increasing strength, by regularity of kappa, if it cannot be isolated by set of less than kappa formulas, it cannot be isolated if it cannot be if it cannot be isolated by formulas, it also cannot be isolated by sets of less than kappa formulas. And therefore, we can apply the situation this Chang-Kissler theorem to obtain the elementary extension. Okay, now what we want to do is to extend the language. So we consider a theory in the logic of the cofinality for a class C, whatever, and we want to start dealing with the compactness problem. So the first thing we do is consider a uniform way of expanding the language. This is something similar to what we do sometimes when we want to quantify elimination in first-order logic. If we don't mind about the way we do it, there is a method by Morley that says define for every formula starting with an existential quantifier, the corresponding, introduce some new relation and define the relation as equivalent to the existential quantifier formula and do it for every formula. And then in this language, you will have quantified elimination. This is the Morley system. We can do something similar for reducing these formulas of the logic of cofinality omega to first-order logic. What we do is to introduce for every formula with a quantifier of cofinality some relation, some new symbol for the parameters. And the meaning in the model will be that the model satisfies the quantified formula with a cofinality, so that they define a set of the corresponding cofinality and linear ordering. So this is called a weak structure. Weak structure is a structure in this extended language. And what you can see is that every formula in the original language using the quantifier of this logic of cofinality is equivalent to a first-order logic in this new language, and conversely. So this is the main idea. This is what basically what Kissler did in his proof. So it's the same kind of idea on what Van Anen also did in his proof. And then we introduce some set of axioms in this language. We call them the Shelah axioms for the logic of cofinality. Well, the Shelah axioms say the following. Well, they could be formulated directly for the logic or for the translation into first-order logic in weak structure. You can do both things. But the Shelah axioms say the following. You have a formula phi with the property that the cofinality is the right cofinality of the ordering. Then phi defines a linear ordering. So this is something you can write in first-order logic directly and without last element. But the important thing comes now. If you have another formula defining linear ordering and you fix some definable connection between them, then the new formula also has the right cofinality. This is something that we know is true in the standard interpretation. So if the cofinality quantifiers have the right meaning, this is true. So these are true axioms in the standard interpretation of the logic. We will take them, we call it SAL, and we will work with them. The first theorem is the countable case of this also was understood and done by Van Anen. You have a countable theory in this logical cofinality, and T together with the axioms has a weak model. So this is first-order logic now, because we are working in the extended language with new symbols. So this is a property. This is a first-order theory that can be interpreted with the other theory of the logic of cofinality. Well, you have a model. This is a particular case, an omega model. So see the class. This is the case of cofinality omega, and has cardinality omega 1. and this will give compactness for countable sets of the logic directly. But this is just one step in our proof of the full compactness. Well, the proof is a standard construction of an elementary chain. We start with a countable weak model of our theory. The language is countable, I said. So this is a weak model, first order, of T union the scalar axioms in the extended language. And we observe that if we fix some linear ordering of the model without the last element, and in the model M0, happens to be that the cofinality is not the right one, then we can apply the corollary using kappa equals omega and using the axioms to make sure that there is a countable elementary extension such that in this order, M0 is not cofinal, but in any other ordering which has the right cofinality, it is cofinal. Because if it has the right cofinality, there can be no connection. So they are unconnected, definable connection between the other one. So the situation is where you have some particular order you want to make it not cofinal, and any other which is not connected definitely should be cofinal. So you can do it by this application of the omitted types theorem that we have seen, and you get a countable extension. And you can take union at limit stages and construct an elementary change of length omega 1 with the following properties. Property 1, if you consider some linear ordering of the union without last element, so the parameters should have appeared in some place in the construction, some M alpha. So in case it doesn't have the right cofinality in M, then this is a construction where you have countably many things to do and uncountably many steps in the construction. So you can arrange that you do everything you need using the remark that we made above. This against standard basic model theory. So you will find uncountably many steps after alpha where this order is not cofinal. So the model M beta in beta is not cofinal in the next model. Hence, you have been adding points to the end uncountably many times, and therefore the cofinality in the order is going to be omega 1. On the other hand, if the order has the right cofinality and has parameters in M alpha, then it's always cofinal until the end, and therefore it has cofinality omega, because it was the cofinality it had in M alpha. M alpha is a countable model. So this is the proof. Whenever you have some linear ordering in a model with this is a model of the theory, and it's an omega model of cardinality omega 1. So whenever the formula that says the cofinality is okay, is right, then it is cofinality omega. And when say it is not the right cofinality and it defines a linear ordering without endpoints, then it has cofinality omega 1. But it is this construction, it's not more than this. Now let's go to the more complicated case of the general case. Now we consider, well, for this proof, we take C to be a non-empty class of regular cardinals, and we assume that it's different from the class of all regular cardinals. So there are two cases that we do not consider. The case of the empty set and the case of all regular cardinals, but you will see it easily that these are trivial cases. So these are not interesting. So the interesting case is this one that we're considering is a class of non-empty cardinals, and not every regular cardinal is there. Okay, then the theorem says that a theory in this logic has a C model, so a model with this semantics corresponding to this class in the sense of the logic, if and only if T together with the axioms has a weak model, which is a first order condition. So if we prove this, we, as a consequence, we will get compactness, because the right hand side is first order. So you can apply compactness to this situation, the first order compactness to get compactness of the logic. So, and this tells you something about completeness of the logic. There's a set of axioms that you can add to the calculus, the shell axioms. Okay, let's go back. Let's go to the truth. Well, from left to right is clear, because you have such a model, then the axioms of shell are satisfied. So the weak model is standard. So you just take the definition as we said, and this is the weak model you take. So this is trivial. Now the problem is, if you start with a weak model of T and the axiom of shell, how do you obtain a model of the logic of the theory T, which with the standard with the semantics given by the class C of regular cardinals? Okay, let's go to understand what we can do. The first thing, well, we start with the assumption that we have a weak model. Then we extend the language in some other direction. This is something we should do because we are going to do a construction of an elementary chain. And what happened is that in some steps, you can get a formula phi with new parameters in the new model that you construct. And maybe with these new parameters, it's going to define an order, which is a linear order without endpoints. So it's new in some sense. You have maybe used the formula phi with some other parameters in your previous model to define some order, and you have control. But now you get a new ordering, and you want to be sure that it's not going to destroy the construction. Okay, so you fix some formula with x, y for the ordering, and set, bar set for the parameters. And what we do is we introduce some new relation symbol of 2 plus 2 times the length of set length arity. And we consider the set of actions saying that if these two formulas with the different parameters C1, C2 define linear ordering without elements with the same cofinality, good or bad, I don't mind, then they are definable connected, and V is the connection. Well, what happened is that this is true in the end of the construction that we did in the previous theorem, because the cofinality there was only omega or omega 1. There were only two options. So if this biconditional is true in that model, then maybe they have the same cofinality omega, or they have the same cofinality omega 1. These were the only two options that we had. Now, choose two cardinal numbers, lambda and kappa, such that we are working with a language which is maybe huge. Kappa should be above lambda, larger than lambda, and moreover, kappa should be larger than the language. And one of them belongs to the class C, and the other one does not belong to C. You see that this is always possible to do in this context. Then my claim is that T, together with the shell actions for this extended language with connections, together with the new axioms about connections, has a weak model, M0, of cardinality kappa, where all definable linear orderings without the last element have cofinality kappa. So all look the same. Proof. Well, the last part about having the same cofinality is easy. So let's think just only in the first part about obtaining a model of this thing. We can assume, because we are working with a first order set of formulas, that by compactness, so we want to check the consistency of something. So it's enough if we look at countable subsets. So we can assume for this claim that the language is countable. And therefore, we can apply theorem 1 and obtain some model M of cardinality omega 1, which is an omega model. Now, as I said, if you have some formula defining with different parameters linear orderings, then and they satisfy this biconditional, then the two orderings have the same cofinality, namely omega or omega 1, because the axiom says that one of them has cofinality omega, the other one, if it's connected, it must have the same cofinality omega. If it has omega 1 and connected, it should have omega 1. This is because of the axioms. Then we can interpret this. There is a connection, between them, and then we can interpret the connection by V. And this gives you a model of the theory, which maybe has not a right cardinality. By standard methods, you can assume that it has cardinality kappa. And maybe you don't know, you have no idea what's going on with the cofinality of the ordering, which are definable there, but you can start. This is the beginning. Then you do the following. You construct an elementary chain of length kappa, where you add a new point in the end for every definable set in the previous ordering in the previous step. So you are always adding points at the end, and you do it kappa times, and you do it for every possible definable model that you get in the construction ordering. So in the end, the cofinality is going to be kappa. Because all models have cardinality kappa, and the unions have cardinality kappa in the end. So this is the way of forcing every definable ordering to have cardinality kappa. And this is our starting point, the claim. We have a model with this property. Everybody has cofinality kappa. And now we do the following. We assume lambda doesn't belong to C, but kappa belongs to C. The other case will be similar. Now we consider some definable linear ordering. So it will remind you the construction in the countable case. You will see. Which doesn't have, consider some order which doesn't have the right property, the right cofinality. So what can we do? We know by these axioms that by the corollary of the main lemma, that we can find some elementary extension where this order is not cofinal, but any other order which has the good cofinality is cofinal. So this is M1, my extension. Now the extended order with the right cofinality has still cofinality kappa, because the previous had cofinality kappa and is cofinal in it. We can assume that the new model has cardinality kappa. And this is the point where we use the axiom escape, because maybe some new ordering appear because we have new parameters. But we're using escape, these new actions, we are sure that it's going to be connected to some ordering with parameters in the previous model. So it had cardinality kappa. So everybody with having the right cardinality, cofinality has cofinality kappa in M1. And the same argument can be used when you reach some limit ordinal to observe that it's still true. So taking union at limit stages, one constructs an elementary chain of length lambda. Remember that lambda was bad cardinality and kappa was the good one. Is that the case? I guess that's what they say. Lambda was the bad cardinality, kappa was with the good one, right? And then we made a construction of length lambda. And remember that we are adding a new point. We can add a new point for orderings with a bad finality. So we do it. Whenever you have a definable linear ordering with a last element, which has the wrong cofinality in the union, and the parameters appear in some alpha, then lambda many times we have decided to make it not cofinal in the next step. But if it has the right cofinality and the parameters are in M alpha, then we have decided to make it cofinal every time. So in the end, it was going to be cofinal in the end. So what happens then? That if you have the wrong cofinality in the union, and this is defining some linear ordering with the last element, then the cofinality should be lambda. And if it has the right cofinality, then it must be kappa. So this means that we have obtained some model with the C semantics of the theory T that we wanted at the beginning. So this is a C model of T. The other case is similar, except that you should at the beginning have all definable linear orderings of well, the model is going to have cardinality kappa at the beginning, but the cofinality of the orderings is going to be lambda. And any other thing is the same, changing lambda and kappa. And then the conclusion is that that we have compactness from this construction, because in the end it has been simulated by the first order logic. One remark: Sheila did not consider exactly the same semantic for this language. What he did was considering orderings that were not orderings of the universe, but every order had some domain. So the formula with a quantifier xy phi means that the cofinality of the ordering defined in this domain, maybe it's not the whole model, has right cofinality. This is the meaning. But what happened is that the compactness of this version also follows from what we did. It's enough to consider in this Sheila situation, you can complete the language adding some relations R and H for each at phi, for each at formula phi, and declare that that you have a corresponding order in the universe R, and you have a connection H between these two orderings. And after adding this information and these new symbols, you can apply the compactness theorem that we have obtained, and you get some corresponding compactness theorem for this version of the language. So I think my time is over. I will finish here. Thanks for